Assalamualaikum warahmatullahi ta'ala wabarakatuh. Welcome to another video on MCTE 2311 Signals and Systems Analysis. In this video, I will talk about Fourier series. Okay, so let's start with the definition of Fourier series. So this definition is from Wikipedia. It says that in mathematics, a Fourier series is a periodic function composed of harmonically related sinusoids combined by a weighted summation. Okay, so I want to take your attention to this word in blue color. Okay, periodic function. So in our course, we are concerned with periodic signal. Okay, so we will see how to represent our periodic signal in form of Fourier series. Okay, we will talk later more on what do we mean by harmonic, and sinusoids function means sine and cosine function. Okay, and these sine and cosine functions are combined with a weighted summation. So we will see later what do we mean by weighted summation. Okay, so let's look back at periodic signals, which we have covered in one of our earlier lecture. Okay, so for periodic signal, it can be decomposed into sinusoids, okay, which is sine and cosine function. For example, let's say you have a periodic signal like this. Okay, so it starts from here and then go here, and at here, okay, it will repeat the same pattern. Okay, so from here to here, you have the fundamental period, the period. Okay, so the sinusoid with the smallest frequency is called the fundamental frequency, and the rest of the sinusoids are called harmonics, which have the frequencies that are multiples of the fundamental frequency. Okay, so let's have a look here. So this is the fundamental frequency, because this signal is the one with the slowest frequency, the smallest frequency, which is 50 Hz. Now we have this harmonic tree, or sometimes you also call the third harmonic. Okay. This signal, its frequency is 3 times the fundamental frequency, which is 50 Hz. Okay, and if you look at the signal here, okay, the fundamental frequency here, within this time range, okay, this signal repeats 2 times. Okay, means it has 2 cycles. Okay. So for the third harmonic here, you will expect the signal to have 3 times 2 cycles, okay, which is 6 cycles. So if you calculate from here until here, there will be 6 cycles. This one, harmonic 5, okay, or the fifth harmonic, this is because its frequency is 5 times the fundamental frequency. Okay, and similarly, the cycles, okay, will also be 5 times 2. So you will have from here until here 10 cycles. So this is what we mean by harmonic. Okay, so the signal with the smallest frequency is the fundamental, and the rest is called harmonic, and their frequencies are the an integer multiplication of the fundamental frequency. So we will look first at one type of Fourier series representation, which is called as trigonometric Fourier series. Okay, so it is defined as the periodic function of frequency omega naught can be expressed as an infinite sum of sine or cosine functions that are integral multiples of omega naught. So I hope you still remember in the lecture, when I talk about periodic signal, I told you that there are three important parameters that we have to know when we talk about periodic signal or periodic function, okay, which are the t, which is the period. This one in second. F naught, which is the frequency in hertz, and this one is equivalent to 1 over t. And the third one we have omega naught, which is the radian frequency, which is given by 2 pi t, and the unit in radian per second. Okay. So if we represent this sentence with mathematical equation, it looks like this. Okay, so the Fourier series of the function f of t, okay, is given by this equation, the sum of cosine and sine function with integral multiplication of omega o. Okay, so you have this 2 times omega o t, so 2 times the fundamental frequency. Okay, so this is the second harmonic. So this one is 3 times the fundamental frequency. So this part here is the third harmonic, or harmonic 3, you would say. Okay, in general form, you can write it like this. Okay, so this AO plus the summation from n equals to 1 until infinity for cos and sine, okay, multiplied by the amplitude AN, BN, and the frequency, okay, multiplied by n over there. So this AO here, also known as the TC part, okay, of the representation, the Fourier series representation, which is simply the 0th harmonic. Okay. This part over here, the whole part, is known as the AC. Right. Okay. And here, the cos and omega ot, and also the sine and omega ot, these are the harmonics, okay, which is given here. You have the second harmonic, the third harmonic, and so on. Okay. And this AO, BN, and AN, these are the coefficient of the trigonometric Fourier series representation, and there are formulas that we can use to determine these three coefficients. However, before I show you those formulas, I just want to show here examples of the trigonometric Fourier series. And so you have here the AC part, which is AO, okay, equals to 1. So here you have a constant of 1. And then here you have cosine 2 pi t, which is this, and you have 3 sine 2 pi t. So this is the two fundamental frequencies, and because they are the signals with the smallest frequencies, which is 2 pi. Okay, so this is omega o, 2 pi. Right? So this is the second harmonic, because the frequency is multiplied by 2, so you have 2 omega ot, which is this signal over here, 2 cos 2 pi t. Okay, so this is the second harmonic, and you can see that for this signal, okay, the cycles, okay, within 3 seconds, the cycles here is 2 times the cycle of this signal. And this one is the 0.5 sine 3 2 pi t. Okay. So this is the third harmonic, because the fundamental frequency is multiplied by 3, and you can see that the cycles, if you count, okay, from t equals to 0 until t equals to 3. If you count the cycles, it will be 3 times the cycles of the sine function here, okay, which is the fundamental sine function. And adding all these signals will give you the total signal that looks like this, which is also a periodic signal. Now let's have a look at the formula to calculate the coefficients of the trigonometric Fourier series representation. And so you can calculate A0, which is actually the first coefficient, is equivalent to the average value of the signal's amplitude and given by this formula. Okay, so you have 1 over t and integrate the function for the whole period. An is calculated using this formula, where the function is multiplied by cos n omega ot and then integrated through the period. For Bn, to calculate Bn, the function is multiplied with sine n omega ot and then integrated through the period. There is another representation of the Fourier series, which is known as exponential Fourier series, represented by this formula over here, okay, which is summation from n equals to minus infinity to infinity, and this Tn is the coefficient that we can calculate using this formula. Okay, so you multiply the signal with this exponential function and then integrate through the period. And these two representations, the trigonometric representation and the exponential representation of the Fourier series, can be interchanged, okay, using these two formulas. So if you have the trigonometric Fourier series, you can change that to the exponential equivalent using this formula. Okay, and vice versa. If you have the exponential Fourier series, you can change it to the trigonometric. Okay, this is the trigonometric coefficients using this formula. Lastly, this is the table that you can use in the integration to determine the An and Bn of the trigonometric Fourier series. And I will show you later in another video where I discuss on some sample problems how you can use this table, okay, in your calculation. Okay, so I will stop here for this video. I will see you in the next video where I will discuss some sample problem related to determining the Fourier series representation of a given periodic signal. Thank you.